Okay, last time we started to look at Lebesgue outer measure, and I'd given you a definition for it. And then we were planning to look at Lebesgue measure. I'd also told you about various things. I'd given you some warnings about the Banach-Tarski paradox, and I told you there was something called the Carrot-Hairdori extension theorem that unfortunately we won't have time to do. All this stuff that you can find in books or in my old measuring integration module. But we had then moved on to give you a definition of Lebesgue outer measure. It was based on a particular kind of half-open interval. We chose half-open intervals that were open at the left. And then we had the obvious notion of length for a half-open interval. And then based on that, here was our definition of Lebesgue outer measure. You look at all the different ways of covering your set by a union of a sequence of intervals of R type. And then you add up the lengths of those intervals, and you've got lots of different ways of doing that. You look among all those sums, you take the infimum. Remember, we're in the extended real line, every set's got an infimum. We're talking about non-negative extended real numbers. The infimum is going to be somewhere between 0 and infinity inclusive. And the only way it can be infinity is if, well, actually there are two ways it can be infinity, theoretically. One is if there were no things at all in the set. The infimum of the empty set is also plus infinity. However, there's always, in this particular setting, there's always at least one way, and in fact, lots of different ways to cover your set using unions of intervals. So this thing can't be empty, but sometimes you can prove that no matter how you cover your set, the sum of the lengths of the intervals is always infinity. Under those circumstances, your Lebesgue outer measure of the set is plus infinity. So it's genuinely taking values between 0 and infinity inclusive. And you get everything in between by choosing intervals of suitable length. And then we had the direct formula without using any of the other notation or definitions or anything, just saying, here you are, look at all the different ways of covering it with half-open intervals, sequences of half-open intervals. Look at all the ways you can add up the lengths of those half-open intervals. That gives you lots of extended real numbers, non-negative extended real numbers. Take the infimum, which you'd like to call a minimum, except that you don't expect to actually find a minimum one. There's not usually a best way to do it, with some exceptions. Like if you start with a half-open interval, and if you are allowing yourself the empty set, which we aren't, then you would just use one half-open interval and take the rest of them empty. You can still fix that actually, in any case. So if you did take a half-open interval, there is a way to do it exactly by choosing a suitable sequence of half-open intervals. So I'll leave you to think about that. Even easier if you allow the empty set in. So some kind of sets you'll actually get an exact value, a minimum for your infimum. Otherwise, you just try to approximate it from the outside. You see, I didn't show, of course, E also may have lots of gaps in the middle of it, and you don't want to cover those gaps. You try to avoid redundancy. So something I may not have made clear last time is if E's got lots of holes in it, you want to try not to cover those holes with your intervals if you can. Of course, you may not have much choice. But if you're doing something like the rational numbers, then, well, there's all these irrational numbers that you'd rather not cover, but you can't help it. Because as soon as you put any half-open interval down, you've got loads of irrational numbers in there as well. So you can't help having a bit of redundancy if you're trying to cover the rational numbers this way. But you just look at different ways of doing it with smaller and smaller wastage, and then you take the infimum, and you'll actually get that the Lebesgue outer measure of the set of rational numbers is actually 0. Okay, you can go in higher dimensions using rectangles or cuboids or hypercuboids, but we're going to restrict attention to dimension 1 for what we're going to say here. But nevertheless, what I say, you can do the same thing in higher dimensions, and that's how you get the Lebesgue measure in higher dimensions as well. Lebesgue outer measure then is defined for all subsets of the real line, even if they are really bad ones. And we'll see there are some pretty bad ones around. So you've got this notion of Lebesgue outer measure, and I called it a measure of size. Perhaps measure was the wrong word to use there, because we're going to see that it isn't a measure in the definition of a measure. But it does somehow allocate some notion of size to every subset of the real line, and it's pretty good, and it does about the best you're going to get. And it turns out you can restrict it to the Borel set. So what do I mean by the restriction? Well, of course, lambda star restricted to the Borel set gives you a map from the Borel set to naught infinity. And of course, it still maps E to lambda star of E, just only for but of course, you then say E's in the Borel sets now. So it's no longer the same function because you've restricted it to the Borel sets, and then it turns out it is a measure, which is part of one of the results I'm going to mention in a moment. And I want to show you how some way towards how you get that result, and that you get a little bit more as well. And as I say, hidden in all there is actually various things. Carrot-Haydory's extension theorem. I'll tell you when we get there, what gets used to prove the result. Right, so in order to understand which sets lambda star is really good on, we need the notion of a measurable set. Before we get there, let me we call something Lebesgue outer measure, but in the literature, Carrot-Haydory has this definition of what an outer measure is. And of course, we haven't proved that Lebesgue outer measure is an outer measure. It's a typical thing like you define an open ball in R to D, and then you have to prove that open balls are open. Well, we define Lebesgue outer measure, and then you've got to prove it's an outer measure. We won't. I'm going to tell you these properties, but you can check these for yourself. So this is C books or whatever for what the definition, official definition of an outer measure is. It's basically anything that's got these three properties that we're about to list here. So what are these properties? First one is it's just like a measure. The Lebesgue outer measure of the empty set is 0. That's a pretty easy exercise. I've made it harder for you though by not allowing you to use the empty set. So you'll have to use very, very thin intervals, length epsilon over 2 to the n, in order to add them up to get less than epsilon, but that's okay. So you can cover the empty set with anything you like, so just make sure you take a sequence whose sum of lengths is smaller than epsilon, and you're in business. So that's easy. Second one, what are we going to call this condition here? Second condition B, what's our name to this? It's something measure satisfies well.
Monotonicity.
Monotonicity. We proved monotonicity for measures using finite additivity, but outer measures don't have to have finite additivity. So this is a property that is weaker, if you like, than finite additivity, given that you're non-negative valued. But it's still something you'd expect for any sensible notion of size. And that's what we get from an outer measure, in particular from the Lebesgue outer measure. If you go back to the definition, what happens is you're taking an infimum of fewer things for the bigger set. It's harder to cover a bigger set. Anything that covers a bigger set covers a smaller set too. So there are fewer ways to cover the bigger set. So you take the infimum of a smaller set. The infimum of a smaller set is bigger than the infimum of a bigger set containing it. So that's the way it works. You just have to go back to the definition of infimum and see how it works with the sets involved. And C has got a name as well that we've already used for measures. Who wants to tell me the name of condition C? What do we call this when we dealt with measures? measure of a union is less equal to the sum of the measures. In this case, it's an outer measure.
Countable subadditivity.
Countable subadditivity, that's the one. This is what you need to be an outer measure. You have to define all the subsets, not just some of them. So you're not just defining some sigma-algebra. You have to define on all of the subsets. You've got to be zero in the empty set, and you've got to have monotonicity and countable subadditivity. And that's already enough for Carrot-Dory's theory to work in order to guarantee that you can find a sigma field on which you're a measure. But how big is the sigma field? Or sigma algebra, I keep calling it sigma field. Remember that if I call it a sigma field, I just mean a sigma algebra. It's just the terminology I used for years here, the sigma field. Sigma algebra is more common. So what are the Lebesgue measurable sets? These are the ones that Lebesgue outer measure will work really well. And, well, a bit of an abstract looking definition perhaps. Somehow, what you're saying here, this statement on its own says that lambda star is working to add up two pieces that make up E. Now, there's some quantifiers involved as well, but let me at least start by drawing E and A. So here's E. Here's A. And then in there is E take away A. And then over here we've got E intersection A. And you can see that E is a disjoint union of these two pieces. Let's have a different colour. So you know that E is going to be the disjoint union of these two sets, these two pieces. If you knew that you had a measure, then finite additivity would mean that these added up correctly. Now they don't always add up correctly because you haven't got a measure. But they'll add up correctly sometimes. For example, if A is the empty set, this is guaranteed to work. Or if A is the whole of X, or the whole of the real line, this is guaranteed to work. I've drawn a two-dimensional picture here, but of course we're actually working the real line, but you know, given this is a general theory of outer measures, really, you could be working in any offset X. Just so happens we're working in the real numbers at the moment. So I've drawn a two-dimensional picture because they're easier to understand than one-dimensional pictures. So if it was a measure, it would work. Otherwise, there are only going to be some sets A that guarantee that this works. So if A equals the empty set or A equals E, this the whole of the real line for us, not E, this is bound to work for all E. And it has to work for all E for A to count as Lebesgue measurable. So to be Lebesgue measurable, you have to split every subset of the real numbers nicely, even if that subset itself is bad. So I'm going to show you a bad subset in a minute, but in spite of the fact that it's a bad subset, if you split it up using a measurable set, it'll be split into two pieces which add up correctly. So that's an interesting feature of this whole construction. So you get that the empty set and R are Lebesgue measurable by this definition. Because they split every set E nicely in a rather trivial way, whereas other, more complicated sets turn out to be Lebesgue measurable for more interesting reasons. And turns out that the set of Lebesgue measurable sets, and this works for any outer measure, is always a sigma-algebra. And that's part of the Karateadori, or the Karateadori theory. So if I combine everything together, here's what you discover. And this is where I hide all of the big theory, and we just don't have time to do it. We look at the set of all Lebesgue measurable sets. So we look at all Lebesgue measurable subsets of the real line, and turns out that it's a sigma-algebra on R. Now that is a general statement that works whenever you've got an outer measure. The set of, whenever you've got an outer measure, you can find measurable sets, and the set of measurable sets is always a sigma-algebra. However, in the special case of Lebesgue measure, you can prove that all Borel sets are Lebesgue measurable. Actually, once you know it's a sigma-algebra, all you've got to do is show that, say, open intervals are measurable. And then you'll get that all the Borel sets are measurable, because once it's a sigma-algebra, and all the open intervals are in it, well, the open intervals generate the Borel sets. So it's enough to check the open intervals. So it's not that hard. So these first two steps, neither of them are that hard, but somewhere in the middle of all this, you've got to use the Heine-Borel theorem about compactness of intervals in the real line. And then Karateadori extension theorem does another nice bit. Well, as I said, you always end up that the restriction of your outer measure to this sigma-algebra is a measure. And of course, once you're a measure on a sigma-algebra, if you take a smaller sigma-algebra, you're still a measure on that as well. So the main meat in this is that if you look at the restriction of lambda star to the Lebesgue measurable sets, so that's from the Lebesgue measurable sets going to naught infinity and of course E gets mapped to lambda star of E. But you restrict attention to F, and so it's now a different function because lambda star is defined on the whole power set, and lambda star was not a measure. But this restriction to this nice large sigma-algebra is a measure. Well, I've hidden all this stuff in there. And of course, okay, then B, remember, is a subset of F. So you can then restrict further by restricting to the Borel sets, and then you get a measure on the Borel sets as well. Now, people use both. So whether you restrict to F or to B, we still call it Lebesgue measure. But some people might call the Borel version Borel measure. But we'll call them both Lebesgue measure. So lambda might be lambda star restricted to F, or lambda might be lambda star restricted to B. And if it matters which of those I'm using, I'll tell you. But often I'll just talk about, oh, Lebesgue measure lambda is a nice example, in which case you can work with the Borel sets or the Lebesgue measurable sets, And most of the time, what I say will work for both. Every now and then, it will be important to distinguish. So there's no difference between lambda of E and lambda star of E if E's a Lebesgue measurable set. They're just the same. Two ways of writing the same thing. But if I write lambda, then I'm talking about a measure. That's the advantage. So note that lambda star is not a measure, but lambda is. That's because it's defined, lambda star is defined on all subsets of the real line. Lambda is a measure. Whichever version we use. Any questions so far? Obviously, I haven't proved everything. So maybe, is there anything you want to ask me about? Well, let me know if anything comes up. Well, to finish this section then, by stating some standard properties that we're going to use in a minute when we show that there's a non-measurable set, a non-Lebesgue set, a non-Lebesgue measurable set. Here's some notation for translates. Sometimes I use C plus A. Sometimes I use A plus C if I want to translate a set around. I honestly don't mind. I've found both in the literature. And if you're dealing with quotient spaces and vector spaces, it looks like you usually write the thing you're translating by first. But in a lot of the proofs of the non-measurable set that I've seen in the literature, people write the thing you're translating by afterwards. So it doesn't matter which way around, it's the same thing. You just want to translate your set, you just move it to one side or the other by you add this constant to every element of the set. It's exactly what you expect translation to mean. On the real line, you've only got two directions to go. If you're going to do this in R squared, then you've got rather more directions, but you're still just adding a vector. And so translation is exactly what you think it means. Now, that last one, which I didn't prove, has got a lot of stuff in it beyond the scope of this module and beyond me setting you to do it as an exercise, because it's got Caratier-Doré extension theorem in, and so on. But this one is a perfectly reasonable exercise. So first bit is that Lebesgue measure and Lebesgue outer measure give the correct value for the length of an interval. So correctly measure, or correctly give the length of intervals. And of course, what are the four kinds of intervals? Here they are: AB, AB open. Oh, that's not a very good one. Do that again. AB closed. I must have forgotten one. Yes, there's open the other end. Now, those are all Borel sets. If we didn't prove those before, it's an almost trivial exercise to check that they're all Borel sets. One of them's closed, one of them's open, the other two are half open, and so you actually have to do something. But it's pretty easy to show they're Borel sets. They're Borel sets, so they're also Lebesgue measurable. We can certainly define lambda of one of these intervals, and you hope that if we're generalizing length, you get the right value. Well, you do, but again, hidden inside there, part of what you do, this is actually part of what you need in order to prove that the Lebesgue measure works in the first place. This is a bit of it. And getting the correct value, proving you've got the correct value really uses compactness there. But at least if you know one type of interval has the correct value, then it's very easy to deduce that the other ones do. by noting that the Lebesgue measure of a single point set is 0. Okay, so then and the next one says, if you translate a set around, you don't change how big it is. Well, that's not a surprise. Perhaps, given it's defined in terms of covers by intervals, and given that if you translate an interval, its length doesn't change, it's not surprising that when you look at covering sets by unions of intervals, the values you get binding the lengths don't change. And that's one of the ways you prove it. There are other ways, I expect, but that's one of the ways you can prove it. So it's almost direct in the definition, in fact. If you've got some intervals that cover one, then the translated intervals cover the other, and so on. More interesting, I think of these, the one that's least obvious how you should prove it, okay, it's actually relatively easy, I'd say, from the definition, to check that if you translate a Lebesgue measurable set, you get a Lebesgue measurable set, is pretty much direct in the definition again, because if you split up a set E nicely, then your translate split up the translated E just as nicely, but you can get any set of the translated another set, and so on. So the Lebesgue measurable one there, the interesting one in here, I think, is that if you take a Borel set and translate it, you get another Borel set. And I'll leave it to you to think how to do that. One way to do it is to prove that the set of things whose translates as a Borel set is a sigma-algebra. And then you can just check intervals and you'll be done because they generate the Borel sets. I'll leave that to you as an exercise. But in either case, the Lebesgue measure of a translated interval is still the same as the Lebesgue measure of the interval itself. Any questions about these properties or anything weird about that? Because that's the end of this section. If not, we will move on and discuss non-measurable, non-Lebesgue measurable set.